Okay, so let's say continue, and let's summarize that in last class, and what we talked about in the plasma is that plasma generate electrons, and electrons interact with a nitrogen, and if you have oxygen, of course, electron will collide with oxygen as well, and this generates a excitation of nitrogen and ABC states. And this ABC states will collide probably with oxygen and then start generate a dissociation of oxygen into two atomic oxygens. And this is also generate a gas helium, fast gas helium, because this energy is much bigger than the energy to dissociate the oxygen molecules. And if you have oxygen in the air, electron, of course, will collide with oxygen and directly dissociate with a two oxygen. If the electron energy is very high, not only you generate this oxygen at the ground state, you probably can generate an atomic oxygen at the electronically excited state as well. So that radical production process dramatically enhance the chain initiation process and participate a branching process as well. So this is that the OH abstraction you can help, and you can do some kind of thermal effect, and due to this a fast gas heating, you generate radicals to produce the few radicals, and for chain initiation to start that chemical reaction. So, and then at Ohio State and also in my laboratory, we try to measure that what is the atomic oxygen production. So using a 2000 laser, a induced fluorescence, a TALIF. So here that is the experiment in Ohio State and done by Jay Woody, and later he worked with me for 3 years. And this is basically showing you that if you have a nanosecond plasma in air, and in air with a ethylene mixture and the lean equivalence ratio and a half, you can see that in air you produce a quite a significant amount of atomic oxygen, I mean O radicals. And then after the pulse stop, and then they decay due to divisional collisional quenching. But in the ethylene process, you can see that the atomic oxygen also produced and decay rapidly, much faster than in the air. What is the reason of the faster decay? So you are combustion guys, and if you have a fuel and air mixture, you generate a radical, which is O, right? What would the radical will do? They collide with each other and then quench it, right? Which is in the air process. Or they collide with nitrogen, generate NOx, probably. And then if you have fuel, likely it will collide with fuel and abstract the H from the fuel, and then become the OH radical, right? So therefore, when you have a fuel inside, and then the radical production, the atomic oxygen decay much faster, at the same time, you accelerate that is fuel oxidation. The faster decay of the atomic oxygen means that the faster oxidation process. And also this that we did the similar measurement in a counterflow flame. We built a counterflow flame and see how that atomic oxygen production affect the extinction limits. As you can see that by increasing the repetition rate, and the atomic oxygen can be produced with 5,000 ppm. And so 5,000 ppm, if we compare to the atomic oxygen concentration in flames, what is the magnitude of O atomic oxygen concentration in flames? 10 ppm, 100 ppm, 1,000 ppm? What? It's about 100 ppm, right? Level in the flames. So, and here you can see that you can measure 5,000, is it 5,000 ppm? 5,000. It's 5,000 ppm. 5,000 parts per billion. I mean, in flames, that probably you can see probably at least 1,000, probably something like that. It's 0.1%, right? More fraction. Probably. If you do a chemical analysis, you can see that. So anyway, so this they try to produce a significant. This is the pure oxygen, of course. It predicts a significant amount of atomic oxygen to initiate the chemical reaction process or to accelerate the reaction. So you can see that the extinction limits of the methane air mixtures will be extended by this atomic oxygen production. So therefore, that the in situ diagnostics of the excited species and the radical production give you some kind of hint what is the major pathway for a plasma-assisted combustion process. So this is the experiment of a OH measurement, and in Ohio State they have a small plasma reactor, and with a quartz tube. This is a DBD discharge, and you put a fuel into it and the inlet, and then this is a probably exit. You try to measure that the hydrogen air and ethylene air with the lean mixture at 100 torr. You can see all the experiment is done at 100 torr. It's a very low pressure. The reason that why do they want to do a low pressure? Because they want to using a uniform discharge, so that they can understand it much better than a arc discharge, which is very difficult to resolve it in laser diagnostics. So they can confirm that by compare that the numerical modeling with OH and then the experimental measurement to some level that of ethylene air combustion process, the model produced reasonably well. But the model produced reasonably well, to a large extent, you can tune the model whatever you want, and in the process. The question that if we don't tune the model, and how good is the model can predict the process? That's the question. And this is a hydrogen air, and then you can see that the modeling and then the experiment, they again agree pretty well, and for this modeling. So, and in this process, because that you really don't know that in this experiment, you really don't know what is the electric field. You can always tune the model, change the electric field to fit the experimental data. So that is so yesterday I talked to you that in plasma-assisted combustion, by using a plasma discharge, you can change the ignition curve and enhance the low temperature combustion, and we can measure that the process. For example, in the plasma, we can measure that the formaldehyde. We can measure the OH and formaldehyde. We can in situ. We can compare with the modeling of plasma. So we talked about yesterday. I don't want to talk again. So in general, that plasma discharge dramatically enhance the low temperature ignition and change that, promote that the combustion process, and from a S curve to a monotonic decrease of the combustion process, and enhance probably the cool flame as well. So I don't want to talk about this. I talk about another experiment at Penn State University, done by a group at Reactor. And he has a small DBD plasma reactor and have a small quartz tube. And then in this reactor, you can see that he heats the temperature from a 600 Kelvin to about 1,000 Kelvin. It's a typical flow reactor. So in a flow reactor, if you don't have a plasma discharge, you can measure that downstream at a different location. What is that? How much fuel is oxidized? How much radical is produced? Right, as a validation of kinetic mechanism. If you believe that the plasma can assist low temperature combustion, if you fire a plasma upstream, you will see a significant change of the fuel oxidation and the intermediate species process. So this is the temperature diagram like this, and then what he did is that he using the 10 nanosecond a plasma discharge. So this the black curve you can see. This is probably the propane and a normalized concentration, and the black line you can see probably is that a thermal reaction. That means there is no plasma. You just heat it and This is a function of temperature. If you heat that reactor until you heat probably 1100 or maybe 1000 Kelvin, and then the fuel start to decompose. And this one is that with plasma at 1 atmosphere pressure, you can see that with a plasma discharge upstream, you can see that the fuel is oxidized gradually and much earlier than a 1000 Kelvin. So this experiment clearly indicates that plasma discharge can accelerate low temperature fuel oxidation very effectively, right? And so this is the graph I showed you, that once you have a low temperature and high temperature reaction pathway, once your plasma get involved, and you can accelerate the ignition process and accelerate low temperature chemistry. I don't want to talk about much. This is cool flame stuff. So this is that plasma pathway. So at low temperature, and your plasma basically generates this kind of atomic oxygen or O1D, excited atomic oxygen. These will participate that the reaction pathway, and you generate excited oxygen. You generate O1D, react with fuel, and you probably attract OH mass fast. Excited nitrogen with oxygen generate radicals, and then vibrational mode may also participate in the reaction, but very few experimental evidence or experimenter has been done to observe what is the vibrational excitation really can enhance the reaction pathway. So you have to be always that in plasma process, electronic excitation and vibrational excitation coexist. It's very hard, very difficult to selectively to excite a vibrational mode and to study that how vibrational mode to react with fuel. Probably laser excitation probably is the best way to excite a single vibrational mode to study the chemistry. I think this is really something interesting area in the future. So as I said yesterday, that we well know that the plasma, air plasma chemistry is well known. The high temperature combustion process is well known. And then the problem that the coupling between these two processes, as the plasma produced species interacting with a fuel at a low temperature, is really poorly understood. So any of the future research you want to propose, you should focus on in this area. This is that the low temperature oxidation or low temperature fuel reforming, that is that the key area that you probably likely to have more contribution. And here that is well studied, and here is also well studied as well. And then these are the kinetic process, and these are the new reaction pathway. We really don't understand what it is, particularly for large alkanes. So how does that excited, for example, molecules react with large alkanes? How does singular delta, vibrational state? There's no certain answer at all in this field. So to answer these questions, and a few years ago, probably 3 years ago, and we tried to develop a plasma reactor at Princeton. So this is that, for example, you have a nanosecond pulsar. You have a electrode, positive and negative. And within this flow reactor, and you can develop this kind of a Harrod cell. And you have 24 pathways, and allow you to detect that the species as time dependently. This is a very straightforward laser absorption spectroscopy. So you can put a quantum cascade laser. You can put for example, a DFB type of laser, and for formaldehyde and for OH measurements. They give you really that the quantitative measurements of time-dependent distribution of this species allow you to validate the kinetic model. So this is the same thing as mostly combustion people do in a flow reactor or sometime in a shock tube, and the RCM is the same thing. So the plasma actually is a nanosecond plasma is 12 nanosecond, and the peak voltage is about 7 kilovolt, and then can continuously run up to 30 kilohertz. So you can study that continuous repetitive plasma discharge, or you can do a single pulse of a plasma discharge and to see what is that the dynamics. So this is the experimental setup. Probably some of you saw it at the a laboratory tour. And this is a quantum cascade laser. There are some other lasers sitting here. And then this is the plasma reactor. Plasma reactor is here. So, and you can, this is at the electrode of the nanosecond plasma discharge. And this is detectors. You can measure the infrared signal. So the plasma discharge is highly dependent on the frequency. So you can see that this is at the, you take a ICCD camera, you get it probably 100, this gate time, 100 nanosecond. You can see that the plasma discharge at a low pressure. If that's 60 torr, normally we do experiment at 60 torr where the plasma is very diffusive and then plasma is very uniform. So allow you to study that the kinetic effect. If you increase the pressure to 1 atmosphere pressure, the plasma probably starts to become a filament and non-uniform. So that data probably is not useful to understand the kinetics, but maybe it's useful in a real plasma reactor, right? So this is at the pyrolysis measurement of ethylene. You can measure the mole fraction as a function of time. So here that is the model, probably the model prediction by this is the measured methane, it's predicted methane, this is the ethylene, acetylene. You can see that some of the species, the plasma model can predict very well. But even for pyrolysis of a methane formation in ethylene, the model really did not do a good job in terms of reproduce the concentration. So this is how the experimental data can provide a key target for model validation. So here that you can see, again, that the oxidation case, that this is the red dots are the experiment of a acetylene, and then the lines are prediction. This is that the blue dots are the water formation and methane formation. Experiment and the model prediction are probably one order of magnitude, several times different here. So therefore, that there's a lot of uncertainty in terms of plasma modeling, even for a simple fuel. And many people just say that, okay, my experiment of plasma-assisted combustion experiment agree with plasma modeling. I really don't believe it. So because they basically tune the parameters and make that agree and show people agree. In research, really, it's not about how much you agree. It's really why it doesn't agree. And how do you make it agree? So really, right? So you understand the process. So don't try to really make the model really agree with the experiment. Rather than try to pay attention why it does not agree, what is the missing reaction pathways. So here that we try to compare that the continuous discharge. We try to run the plasma with a continuous discharge. You can measure that using for example, a GC, a micro GC. We can measure laser-induced laser absorption spectroscopy. We try to compare them, that whether they can get the same number using laser absorption or using GC. You can see that for many of the species, we measured by GC and measured by that laser absorption, they get the same number. So therefore, the uncertainty really is not that the uncertainty of laser measurement. It's really uncertainty of kinetic models. So later we try to update the kinetic models. You can see that when you listen to Dr. Stephen Clifstein's lecture, he says that, okay, my high-level quantum chemistry computation give you the uncertainty of 30%, right? They say that 30%. Where does 30% come from? So one of the major uncertainties is the energy barrier, right? There is some uncertainty of the partition function, right? The energy barrier, the accurate method of what they can do normally today is probably 1 kilocalorie per mole or half kilocalorie per mole. 1 kilocalorie per mole at 1,000 Kelvin give you uncertainty about how much? One kilocalorie per mole give you how much uncertainty? No one tried to estimate at 1,000 Kelvin? So if you look at the Annus law, exponential function of E divided by RT, right? Correct? So if you have a 1 kilocalorie per mole here, 1 kilocalorie per mole is 1,000 times 4.18, that it becomes a joule, right? And divide by the 8.1, 8.31 or 8.1? 31, right? And then this is at the 1,000 Kelvin. So if you see this one is about the half, 2. This one, they cancel each other, the E to the half. You calculate the uncertainty at 1,000 Kelvin, 1 kilocalorie per mole, uncertainty E to the half, how much? Yeah, square root of E and inverse it. 50%? Roughly 50% uncertainty. What? 60%. Okay, 60% accurate. Thank you very much. 60% uncertainty. If someone can predict this one by a half kilocalorie per mole, and then you're down to 30% uncertainty, right? That's what Stephen Klipstein is claiming. But what if my temperature here is 300 Kelvin? You are in big trouble, because this thing will be increased by 3 times, right? So your uncertainty actually grows 3 times. 60% becomes still factor of 2. So there's a lot of uncertainty of the reaction rate for plasma, low temperature plasma combustion, is because that it's very difficult to computationally predict that the energy barrier accurately. But as the temperature decreases, the uncertainty exponentially grows. So that's the problem. So experiment is the key to understand what is going on. So next thing we try to do is that we try to develop a new kinetic mechanism called HPMAC. Most of the reactions we put it there are taken either from quantum chemistry measurement or from quantum chemistry computation, and have the uncertainty down to 300 Kelvin, and including the low temperature pathway. So this high pressure mechanism I developed at by my postdoc before was Xuelian Yang. He came from Argonne lab. And right now I put it on the website. You can download from my website. So you can see that this is that they measured the species of methane and water. They dramatically enhance that the predictability compared to USCMAC. You can see the USCMAC, that this is that the measured water. And measured water is here, and predicted water is here at 300 Kelvin. So you can see that it's about more than an order of magnitude different. And so therefore, USCMAC particularly is an optimized kinetic mechanism. You cannot use it beyond the temperature range being validated there. So for plasma mechanism, the better to do is that the elementary rate-based kinetic model, so that you know what is going on. Do not using an optimized kinetic model try to explain the phenomena, because it's beyond the temperature range, and your mostly combustion model are validated and developed. So what is the key difference in terms of HPMAC and compared to a USCMAC? So this one, for example, if we have ethylene, that you have plasma in action with a argon. So the argon ions collide with this fuel. You generate a lot of fragmentation of pyrolysis, and from this energetic atoms. And also you can generate the radicals. That radicals attack the fuel and generate the small radical. This is all high temperature chemistry that is already included in either USCMAC or at the HPMAC. But it's very interesting at the low temperature. If you generate this kind of OH radicals, the OH radicals attack to the fuel molecules and add another molecular oxygen and form a formaldehyde, and then generate this RO2 chemistry. This is a very typical low temperature chemistry. It does not have it in, normally it doesn't have it in ethylene, but you have low temperature with plasma, and this low temperature reaction pathway is very important. So therefore you have 3 different reaction pathways. Is that the pyrolysis and dissociation with energetic electronically excited molecules. You have a H abstraction by the radicals produced by the plasma, and you have the low temperature oxidation process due to that the plasma activate a low temperature reaction. And then even though that the model can produce good with that some of the key product and reactant. But if you try to compare with that the time-dependent measurements of that the formaldehyde, for example, this is the experimental measurement, and this is the model a prediction. Still a factor of maybe 4 different in terms of magnitude of intermediate species. The reason is this: for example, you have methane, and the plasma not only produce O, but also produce O1D. This O1D reaction can directly form and formaldehyde with a methane. So this reaction channel, the reaction rate of O1D reaction with that, for example, a methanol radicals, and also directly with methane, the reaction rate constant here is not well understood as well. So I think that is someone really for quantum chemistry people, and I think this is some area somebody has to pay attention to. For example, methane leakage to upper atmosphere, and the methane will be mostly oxidized by what? By OH, right? You take probably 15 years to clean up the methane in upper atmosphere due to but if we have a O1D formation, ozone, right? UV photon collide with ozone generate O1D. That O1D will react with methane as well. That participates in the oxidation process of methane. So this is not combustion, it is at the upper atmosphere chemistry as well, right? If you do the shale gas, you leak a lot of hydrocarbons, O1D will participate in that oxidation process. So what is the reaction rate? Somebody has to measure it, and then there will be a big impact, not only in plasma combustion, but probably also impact atmosphere chemistry as well. So the next thing that, what about the large hydrocarbons? The large hydrocarbons is really totally a mess. So last symposium we presented a paper that they tried to measure that the oxidation of a N-heptane and in a plasma reactor. So this is that the mole fraction of formaldehyde measured in the experiment of stoichiometric lean mixtures. And this is that the model prediction, just extending the existing model by using the same rate ratio method to extend that the ethylene model to N-heptane. You can see the formaldehyde prediction is 10 times probably lower than what it should be. See? So there must be missing pathways we really don't understand, and we really don't know what it is there, right? So why we don't know? It's because there's no available cross-section area of electron impact with the fuel. So in air atmospheric chemistry, we know the cross-section areas of electron with these molecules. And then in for example, fuel, up to probably C4 and probably for pentane, some of the cross-section areas are available. And this is for oxygenated fuels. And for large alkanes, and this is empty. So there's no data around this available there. So I think that if you are interested in plasma combustion, I think that you should do this area, and rather than rush into that area, you want to do something that does not exist, and instead of doing something already exists to try to improve. That's important, but something not exist is the first priority to do it, and it's also application driven as well. Most of the fuel are either methane, propane, or some kind of large alkanes anyway. And another thing that if you're looking at the low temperature chemistry, many of you, and if you're working on internal combustion engine, you're worried about the low temperature chemistry. For example, if you have a few radicals and you have oxygen, and they generate oxygen add to the few radicals generate RO2, right? This RO2 isomerize it and become QOH, and then they decompose to different products depending on the potential energy surface. So you have 1, 2, 3, probably 4 different potential energy. So normally, if your oxygen is ground state and you coming from here, you probably mostly produce OH plus RO, probably the most favorable reaction channel for that RO2 chemistry. But if you have a plasma process and your oxygen probably is initially already electronically vibrationally excited, this is not a ground state anymore. It is an excited state. You can this RO2 complex can be anywhere between. If it can be anywhere between, they could go to this channel, they go to that channel. You totally change the branching ratio of that the RO2 decomposition. So what is that the vibrational oxygen interaction with RO2 and form this Clark's? I don't think anyone they did it. So if you are quantum chemistry people, I hope you do this computation. If you are experimental person, if you design experiment, you can detect the reaction pathway for the simple fuel, dimethyl ether. Tell us what is that vibrational excitation of oxygen, and this is really a science problem, right? It's very, I think that's very interesting and unanswered. If you have vibrationally excited in this non-molecular, oxygen is attached to it, how that the RO2 is going to decompose? What is the potential energy surface? So I think that is interesting. For me, at least, I'm curious that what is that we can do in this. And recently, that we developed this for a photoless reactor, and then using that the YAC laser to pump that the ozone to generate a O1D, and then we flow the fuel into the reactor. We try to do a time-dependent measurement about how does O1D react with the fuel. For example, the fuel we try to look at, for example, ethylene or large alkanes if possible. And with the measurement, we can do a direct laser measurement between the two laser absorption cells. And then we can also do some kind of thing, a HO2 measurement and an OH measurement by using a Faraday rotational spectroscopy. But the research is not that simple. It takes about several years. And right now, we finally get some signal, at least, but we have not been able to quantify it. So one of the results I'll try to show you that the experiment, if the O1D reaction with a methanol, you have OH abstraction, you can form that a methanol radical plus OH, and you can form this these radicals and plus the H radicals. This is a typical reaction pathway. But if you do this, and then you numerical model basically give you the black line, it does not fit that reaction very well. But until you find that a different reaction channel, that is the O1D, inserted into the CH bond and directly form the formaldehyde and water. So this really can be confirmed. And Xuelan Yang, and when he worked at Princeton, he computed that the quantum chemistry and the reaction pathway. You can see that most people consider about this reaction pathway, but indeed that the O1D insertion into methanol radical fuel can generate a low energy barrier to directly produce a formaldehyde and then water. So this really reminded me that why that from N-heptane, that the measured formaldehyde is 10 times bigger than the predicted formaldehyde. It's probably because that we don't have appropriate O1D reaction with methanol, with N-heptane fuel. How that oxidation produce some kind of directly produced formaldehyde, probably from that oxidation process. And we don't know that reaction. So one thing I try to show you that's a Faraday rotational spectroscopy. And there are different groups, and they try to develop this. And here at Princeton, we collaborate with Girard Wasaki at electrical engineering. So measuring OH and HO2 is very important and in combustion process. And particularly at the low temperature, because the OH concentration is very low, and HO2 is very important to in low temperature chemistry. But measuring these two species are very difficult in laser absorption because they directly overlap with water. The OH bond basically the same as the water OH bond, stretch so therefore that if you have water is formed, and then you have no way you can measure this by laser absorption. So the way that we developed it is to try to introduce, let's say this is that the HO2 molecules, and you have a laser come in. If the laser is polarized, and then polarized, it generates a polarized laser electrical field propagating in this a laser direction. So in order to measure HO2 instead of measuring water, and you need to this is absorption and dispersion line about the water and probably HO2. And you want to perturb the electronic orbiter by external magnetic field. So you put a magnetic field at the same direction as the laser propagation direction. Therefore, with the electromagnetic field perturbation, an electron orbiter could be changed. So this energy, ground energy, for example, here is J equal to 3/2. So the degeneracy should be 2J plus 1, right? So it should be 4. So you can put a magnetic field, this energy level will split into 4 levels depending on the rotation of these electrons. And at the same time, the upper level is also split into 4 levels. And then the selection rule basically said the absorption between the ground and the upper level now is dependent on the rotation of the photons. Before is not, but now it has to be because that the angular rotation momenta is split. So therefore, that if you put a laser that polarized with the left-hand side rotation, with the right-hand side rotation with the same magnitude, you are linearly polarized in that laser. So after you pass in this HO2, a left-hand side, for example, right-hand side rotational photon will be absorbed more than the left-hand side, rotational polarized photon. So therefore, the polarization angle initially is 45 degrees. After you pass this HO2, and then polarization angle should be either bigger than 45 degrees or then less than 45 degrees. So that change of polarization angle will proportional to how much that HO2 is there. So this is the measurement of HO2 in a flow reactor. So if we have a flow reactor in a steady state flow, you can using I think the 3 paths, going, reflecting, and go back. The 3 pathway, you can measure the HO2 and to a 1 ppm level, and the OH probably is 20 parts per billion. Very sensitive to measure in a flow reactor. The difficulty for us right now is to try to measure time-dependent measurement. There is difficult because you have to get a 10 kilohertz time resolution to measure the time. Most of the reaction kinetics stop at 1 millisecond probably in a flow reactor. So you have to have at least a 10 microsecond resolution. So that is something we try to do, and right now I thought that we got some signal and a few weeks ago, and we are now be able to measure time-dependent HO2, and at least in the photolith reactor. So if that is quantitatively verified, and we probably get some meaningful data for O1D reaction with fuel, and how much that formaldehyde, how much HO2 is formed in the process. So that is something we are doing and in the laboratory. Well, it will take some time for us to do because this new method is already difficult to do because the background noise is very, very large. So the time-dependent measurement is difficult is that you cannot modulate the magnetic field that fast. So normally for steady state, you don't have to modulate. You can modulate the magnetic field with 10 hertz to eliminate the background noise. But if you want to do time-dependent measurement, the modulation of the magnetic field is not 10 hertz. You have to modulate 100 kilohertz. That's the difficult part for the experiment. Okay, so I try to introduce you some of the basic methods about how to measure the plasma physical properties and how to measure that the species and in a flow. I think that the other courses of Professor Dreisler probably teach you more about the PLIF, laser absorption, this method. But this one probably is not something, the method you see routinely in combustion diagnostics. So, okay, so what I try to say that a time resolved and a spatially resolved in situ laser diagnostics of electrical field and electron number density, electron temperature, excited species greatly enhanced our understanding about the kinetic process in probably the last 5 to 10 years. And production of O and O1D, singular oxygen, electronically excited nitrogen, and vibrational nitrogen are the important process in combustion enhancement. And there are fast and slow heatings in plasma. They are important, but if you want, in order to understand that, the energy transfer between vibrational, and vibrational-rotational are quite complicated in that process. Plasma really activates low-temperature chemistry and enabling low-temperature combustion and cool flames. And then electron impact cross-section areas for large alkanes. And the reaction rate involving O1D and other excited species are poorly known, so in this area. So also that the effect of vibrational species excitation is not well known, understand. So this is something I try to share with you. What is the state of the art in terms of research and in plasma field, okay? So once you have experimental data, and then your experimental data is always limited to a certain condition or to certain species, right? So if you want to understand the whole process, and you need to have a basic model capability to model plasma cystic combustion. But in combustion process, you probably can download from Chemicking. You run a Chemicking, and then you compare that the species time dependency with the experiment, and you publish a paper and do a sensitivity analysis to tell people what reaction is important, what reaction is not important, what reaction rate should be modified. So that's the typical reaction. But in plasma combustion process, the plasma modeling is rather more complicated due to that the time scale. So in order to help you to provide a simple tool to model that the plasma process, just like a Chemicking you have in combustion, I try to give a little introduction about that what is going on in terms of a plasma modeling. So some of the slides are prepared by Xinqiang Mao, and probably he's sitting here. So if you have any question, you probably can ask him. But he's doing that the plasma modeling about the nanosecond with the DC discharge. So plasma process is a rather complicated in summarizing that involving this electronic excitation and vibrational excitation, and then dissociation and excitation, and ionization process, and then ionization, dissociation, and then attachment, and so on. So you have many, many processes. And which process is important is really highly dependent on what is that electron energy. That electron energy is governed by E over N, right? So this E over N called electrical field strength. That is governing that the electron energy. Even you have electron energy, the electron is high energy and collided with molecules. But some of the molecules has very large cross-section area for reaction. Some of the molecules don't. Even for the same molecule, and the cross-section area probably is a function about your electron energy. Low electron energy does not make the reaction happen. High electron energy probably makes the molecule to dissociate. And then intermediate electron energy probably makes the molecule to excite, right? So this is a process that you can see. We showed you yesterday that for methane, oxygen, and helium mixture, for example. And this is at the E over N in terms of Townsend. This is the energy loss fractions, vibrational excitation of oxygen and methane, and the oxygen dissociation somewhere here, and ionization somewhere here, and then a methane dissociation. So these things, this is highly dependent on electron energy. In order to calculate the reaction rate, what information you need to do? You need a cross-section area, right? and you need energy distribution function, right? And then, so then you have to integrate them and get the reaction rate. So the first thing you need to do, you need an energy distribution. What is the energy distribution? Electron energy distribution. How do I know electron energy distribution? Yes, you have to solve a Boltzmann equation to get an electron energy distribution. Once the electron energy distribution you know, and you know the cross-section area, you integrate them, you get the reaction rate. So that is a plasma process. So if I have a distribution function, and I know the cross-section area, I integrate them for elastic collisions or inelastic collisions, I probably can get a reaction rate. This is the plasma process. Fortunately, there is a solver called Boltzmann solver. The Boltzmann solver is commercially available, probably right now probably is free. You can download, and you can input that the E over N. You can input that cross-section area. You input the mixture composition, and then can tell you what is the electron energy distribution function. After that, you can integrate this one, probably give you reaction rate as well. So that is the current state of the art, and people doing that. I showed you this before. These are the cross-section areas. If you're doing some mixture using this one, and you can download the cross-section area either from in papers, from database, but if it's not, and you have to scratch your head and try to making your own cross-section area with some kind of experimental validation. Okay, there's some NIST database give you electron impact, a fragmentation process that give you a guidance about what is the speciation and probably cross-section area as well. So let's say that I show one example is that electron impact excitation reactions. So electron impact with a molecular and electronic excited, and the important reactions we showed you two. One, electron impact with nitrogen generate electronic excitation of nitrogen. Second, electron impact interaction with oxygen generate thus a singular delta and B sigma and all a high energy level excitations. So the energy level is showing here, depending on what is that electron energy here. Lower electron energy is generated singular delta. High electron energy is generated nitrogen ABC. Because electron energy number density is very small. In plasma combustion, mostly you worry the electron impact with air, right? Nitrogen and oxygen, and plus electron impact with fuel, right? These three reactions, set of reactions are important. So this one, if you know that a distribution function cross-section area, they can do the integration, and you can calculate what is the rate constant. And Boltzmann software will provide you and this rate constant for electron impact reactions. Okay? And this is the cross-section area as an input, and you give into this, and then they give you a reaction rate. So this reaction is important because that you can see H plus O2 reaction is governing chain branching reactions. And then if you have a electronic excitation of oxygen and a nitrogen excitation, electronic excitation, they bypass this reaction, they generate radicals, create a new reaction pathway at the low temperature by plasma. So this is how that electron impact excitation reactions contribute to plasma-assisted combustion. In a chemical vapor deposition CVD process, plasma-assisted process, pretty much that the electrons impact that the silane molecules, for example, a methane molecules that generate a carbon nanotubes or CVD. That is the same process. We don't call plasma combustion, it's a low temperature plasma reaction process. So plasma-assisted combustion, I think, is a great bridge to bridge you well understand combustion field to many, many other areas, okay? Because combustion process is always high temperature. High temperature is only limited to thermal systems. But plasma can be high, can be lower, and then the reaction rate kinetics is similar to what we learn in combustion, right? So we can penetrate the knowledge of combustion using a plasma-assisted combustion as a bridge to other areas. So that's when I come to Princeton, I decided that this is some area I want to go because it's so new and nobody understands what is going on. So I try to be one of them to understand a little bit. So that will be push that field forward, right? So, and so the next thing that is the electron impact dissociation. This is the second important reactions and in the plasma process is the electron impact with oxygen. And if the electron energy is lower, and then you dissociate this one into two atomic oxygen at the ground state. If the electron energy is high, you could generate a one ground state atom, and the other one is electronically excited, O&D, or is a singlet S state. So it depends on the electron energy. And then for methane, for example, electron impact can generate many things and depend on that the electron energy as well. So if you're looking at the energy threshold, this is that of a 6 eV, and you dissociate to two atoms, 6 eV, remember. So when talking about the plasma-assisted combustion for oxygen, 6 electron volt to dissociate this guy. So dissociate nitrogen, you need a much higher energy to do that. So, and then this is that if you have a 8.5, for example, electron volt, you can generate O plus O and D. And then this, so if you have 100,000, then you can produce these kind of things with 100,000 and in a plasma process. And so for a lot of energy, you can directly generate a carbon directly by colliding with methane. You can generate H radicals and CH. So it's a lot of, this is the process probably involved in the methane reforming process. And how do you optimize the electron energy to generate that the syngas you want? This is the cross-section area, and I showed you before, and to dissociation and with the excited states, and then all this database are available, and in literature you feel free to use. So the next thing that is ionization process. This is the process that electrons basically collide with molecular and generate ions and electrons. So this process in combustion process, to me, I think mostly is gas heating effect, and then controlling that the electron number density. If we don't know this equation, you don't know how much electrons is produced. And if you don't know that so the ionization process. So this ionization process is governing that how much that the electron number density is produced. Okay, so it is a very important reaction. But at the same time, this thing in the end is governing that the gas heating. If we have more ions generate electrons in recombination, they generate fast heating. So this is at a threshold. You need a very high electron energy to initiate these reactions. So this is cross-section area available, and those that are affecting that the combustion process, for example, recombination, they generate a gas heating. A nitrogen ion collide with methane, they produce generated radicals, and another radicals are methyl radicals. So these are the process that the electron impact ionization process can potentially affect your combustion. Another example that attachment reaction. Attachment reactions also is the opposite of ionization. They're basically losing electrons. So this reaction rate governing that, also governing that how much electron number density decay when your plasma is off. But the electrons will attach to the oxygen molecules. For example, the negative oxygen ions and can react with H. We generate compared to H plus O2 reaction. This is 5 orders of magnitude faster, and compared to this reactions. So there are so many reactions in plasma-assisted combustion. They might potentially impact the radical production process. And here that the electron impact is vibrational excitation. So if you're really worried about heating, and you need to consider vibrational process. And if you probably worried about that low temperature combustion involving vibrational oxygen, and when electron energy is low, then you have to worry about this process. At high electron energy, this reaction does not exist because the cross-section area is very small. At high electron energy, this reaction is the dominant reaction that produces a lot of vibrational excitation. So with what conditions, which vibrational excitation you need to consider, and that is a question you need to consider. For example, that the methane vibration. This is someone we want to study in the future because we want to say that the methane reforming, particularly that if we have methane, if we have a catalyst, right? If your catalyst to reform methane to syngas, you need to heat to very high temperature. And the catalyst probably will not stay very long, and then you need a lot of energy to heat that thing for reforming process. And the idea recently, more people try to say, can we using a plasma coupled with catalyst, then can dramatically reduce the reforming process. You don't need to heat probably 1,000 Kelvin for the reforming. Maybe 600 Kelvin, 700 Kelvin is good enough if you have plasma. So what is the plasma process? If a plasma just generates radicals, it's not a good reforming process. You want in the plasma to generate, for example, vibrational methane. That vibrational methane with very low energy. What is the energy for vibrational methane? Is here. That you see is 0.4 or 0.2 electron volts. So that vibrational methane probably stick with the catalyst. Probably directly you need to dissociate, and then go into hydrogen formation, right? So the question is that how much vibrational methane is generated? How do you quantitatively measure it? Right? Vibrational methane. So that's the key question and to be answered. So we need to model and know this reaction to model and detect this species so that we can generate a good model to predict that the low vibrational excitation. There have been a lot of study before in terms of a electron impact or excited molecular impact, vibrational excitation. These vibrational excited molecules, they using vibrational transitional relaxation to generate heat, or they generate a vibrational relaxation to go from a higher vibrational level to lower vibrational level, and or they collide with molecular, maybe generate some kind of chemical reactions. So these are VT, VV, and then the collisional reactions basically are the relaxation process of energy. And how do we compute it? Well, there are many classical models developed. This is not a well-developed area. Highly dependent on the people knock their head and then build a model for people to use. And I think that the quantum chemistry developed today in combustion area is really can make a contribution in this area. Okay, I think that knowledge should be transferred from the lot of research investment in combustion to develop this wonderful tool. We should be able to push to the area of this area and generate impact to adjacent research area. Okay, so I think we take a 15 minutes break, and then I come back to talk about this empirical